Alright, so in this video we're going to be going over the initial idea of how to insert into an AVL tree. One thing I wanted to make sure to point out is that it's going to take us the next 5 videos to actually go over the full insert algorithm. So I'm going to be just talking about it in little pieces as we go. So once this video is done or the slide deck is done for this particular video, it's not going to be a complete insert algorithm quite yet. So we're just kind of introducing the idea. So again, an AVL tree is a binary search tree that has an additional condition, and that condition is that if you take any node in the AVL tree, it must satisfy the condition that both of its subtrees, its left and its right subtrees, can only have heights that differ by at most 1. So for example, if we look at this node, 29, in this particular tree, the height of its left subtree is 0, the height of its right subtree is 0, so the difference is 0. So this particular node satisfies the AVL tree. If we look at 46, its left subtree is 1, its right subtree is 0, so the difference is 1, so that satisfies the AVL condition. And an AVL tree is an AVL tree when all of the nodes in the tree have that condition satisfied. So what we're going to be doing is looking at the algorithm of how to insert into an AVL tree and maintain that condition, basically. So let's say that we were inserting into this AVL tree and we were placing 50. So 50 would go here in the AVL tree. So if we put 50 here, what would we have to do? Well, we'd first have to update the heights. That's kind of the easy part. So the height of the node that I just added would be 0. I would have to update this one to 1, and then this one is going to stay 2, so that one's okay. Updating the heights, we'll look at that algorithm in a second. But what you also have to do is then recheck that all of the nodes that you just changed still satisfy the AVL condition. So this node is fine because we inserted it, and it has 2 null pointers, and so those are both -1, so the AVL condition is satisfied here. We'll want to check 76. So 76 has a height on the left is 0, height on the right is -1. So the difference between that is 1, so that's satisfied. And then we have a difference of 1 and 1 when we check 46, so that's a difference of 0. So when we added 50, it maintains its AVL tree conditions. If we wanted to add something like 45, so 45 would be inserted here. This would be 0, this would be 1, and this would be 2, and this would be 3. We would want to recheck all of those nodes to make sure that it's still balanced, but we can see pretty easily right away that 46 is definitely not balanced because this is a 2 and this is a 0, so the difference is 2, so the AVL condition is broken. So we're not going to, in this video, talk about how to fix if an AVL tree is broken. We'll talk about that in the next couple of videos. Basically, you have to do all these rotation algorithms. But we're going to talk about how we can update the heights in this video. So when we write the insert function, the first step is to insert the item. And so let's go to the 45 example that we were doing before. So if we insert 45 here, the first step is to basically just find where to insert 45. When we do that, we're going to need to keep track of the path that we took to insert 45. So That was the path that it takes in order to find where 45 should get inserted. The way that we do that in code is that we create a stack. So when we are running through the search algorithm, we're going to add the nodes onto the stack. So we're going to get 46, 29, 31, and 45. So we basically have a way to trace, where we've been, so that we can go back and update the heights. So that's the only additional change to the insert function from a regular BST, is just keeping track of where you've gone. Otherwise it's the same code. You search, compare left and right and go the right direction. So then what you have to do is then walk back up the tree. So we've done it a couple times now. So this is going to be 0, this is going to be 1, this is going to be 2, and this one is going to be 3. So how do we do that? We do that by going through this stack that we created and popping off the stack. So you're going to pop the first one off the stack, and then you're going to calculate each node's left and right heights. So to do that, you're just going to access its left height and its right height. There is an edge case here, right? If the node doesn't have any left and right children, so the first node, the one that we just inserted, doesn't, right? Because it points, both of them point to null pointers, then you wouldn't be able to go to their left and access their height. So instead, you're just going to set -1 as the height if the left pointer is null. And then, so you get the left height, you get the right height, and then to get the new height of the node, you're just going to take the max of those two values and add 1. So with the 45, we pop it off. Its left and its right are both -1. We add 1, so we get a height of 0. So it's just doing what I just showed you, when I did it by hand in code. And then once you calculate it, you'll just set that node's value appropriately. One thing that you might observe is that, and then you keep going and popping off the stack as you go and updating along the way. One thing that's nice is that you only have to do this until the heights stop changing. So you might not need to go all the way up to the root of the tree. So once you have calculated a height and it's the same as what it already was, then you can stop updating heights. So an example of this would be, let's say that we inserted 150. So this would be 0, and we know that because we would go to its two children. Those would both be -1. The max of -1 and -1 is -1, plus 1 is 0, and so you get a height of 0. Then you would go up, and again you would check 100's left and right child. Its left height is -1, its right is 0, the max of that is 0, plus 1, you get 1. And then you would go up to 76 and check its children. So here you would get a max of 1 and 1, which is 1, plus 1 is 2. So here 2 doesn't change. So if it doesn't change, you basically are done because nothing above it will change. So you're just going to break out of the loop at that point and all of your heights are going to be updated. So that's kind of the first step of insert. The first step of insert is to search the tree as normal, figure out where you need to insert, keep track of where you've been, then go back up that path using that stack of nodes and find each of the heights of the subtrees of each node, max, plus 1, update, update, update. You can break out early if you find that a node's height doesn't change. That is it for our introduction to insert for an AVL tree. Next up, we're going to talk about now what to do if the AVL condition is broken.